introduce our next speaker, is Sergey Levine, who's at Berkeley in Department of Electrical Engineering and Computer Science. He's a PhD grad from computer science at Stanford. And he works at the intersection of control and machine learning. So it's a nice theme for this week. And he's a great publicist for the field with lots of media coverage of his work in places like New York Times and Bloomberg Business. So, okay.
All right, thank you very much for the introduction. For today's talk, what I thought about what to talk about, since I'm coming in kind of at the end of the of a week-long workshop on this topic, I figured, so much has already been covered that I should pick something a little different to hopefully keep people entertained. So I decided I'd make this, it's a little bit of a Frankenstein kind of talk. It has somewhat distinct parts stitched together, but I want to do that because I actually want to point out some similarities. Maybe these similarities are kind of obvious to a lot of you between what might conventionally be seen as two fairly different topics, offline reinforcement learning and model-based optimization. And I wish I could tell you that these ideas in some really interesting way to develop better algorithm. I haven't actually done that yet. So I'm just going to talk about the two parts separately, but hopefully I'll present it in a way that will make the connections obvious, and maybe you can figure out how to combine them to get much better algorithms. So don't expect me to tell you how model-based optimization can revolutionize offline RL, because I haven't done that work yet. But that's kind of the point of a workshop like this, is to kind of stir up some of these ideas. All right, so, and don't worry if you don't know what model-based optimization means. I'll describe it in a very biased way in a second. But to start with, let's start with kind of a somewhat big question and a simplistic answer. What makes modern machine learning work? Well, maybe at a very, very high level, what makes modern machine learning work is the availability of very large data sets and very large and high capacity models. So we've seen that this basic recipe works really well in a range of supervised learning fields like image recognition, translation, speech recognition, and so on. So maybe, as long as we have large data sets and large models, we can get things working well. And we've seen that predictive models trained in this way can be very powerful, not just for computer vision and NLP, but also domains that might more conventionally be viewed as decision-making domains. For instance, this is a paper from FAIR, from Facebook AI research, on predicting the functional properties of proteins, right? So this often goes hand in hand with decision-making problems, like maybe you want to select or design a protein to do something. They're not doing that in this paper, they're just predicting the properties. But the insinuation is that if you could train these predictive models, you could perhaps design proteins to do something. And those of you that heard about the recent result from DeepMind on protein folding, kind of similar story. A big part of why people care about that problem is not because they want to solve the prediction problem, they want to actually solve the decision-making problem of selecting a design that has a particular functionality or a particular geometry. Another data point, work on medical imaging, right? So medical imaging is in service to a decision-making problem. The point of doing medical imaging is to make a decision about what treatment to administer. Now, in the academic world, the research in this area is more concerned with, can you actually make an accurate prediction? Can you, take an X-ray of someone and predict whether they have pneumonia? Very timely, very topical thing these days. But the reason people are excited about this is because it's eventually going to be in service to decision-making. But this is all work on predictive model. There's no decision-making actually being done in these works. There's also work on decision-making separately from this in the community. And we've seen that automated decision-making is, of course, very powerful. Everyone here is familiar with this, that you can set up a reinforcement learning algorithm that can play video games, control robots, and beat world champions at Go. So one might hope that somehow these things can be combined, and you can have reinforcement learning algorithms that can, diagnose people with pneumonia and decide on a course of treatment, or design, proteins to act as drugs or what have you. So, obvious question is, can we put these ideas together and can we make things work really well? So can we actually use the model that we trained in this way with reinforcement learning for things like, courses of treatment for patients, designing drugs, what have you, and controlling robots. So what could possibly go wrong? What's the problem with this notion? Well, there are two problem settings that I'm going to outline, and I'm going to claim that these problem settings are actually very deeply related. Then I'll describe a problem that they have in common. And then I'll describe some algorithms that, as I said before, unfortunately address these two problems in isolation, but hopefully are suggestive of ways to put them together. So the first setting is offline reinforcement learning. So conventional reinforcement learning is viewed as an on-policy process where you have an agent interacts with the world, collects some data, improves its policy, and then interacts with the world some more. Off-policy RL extends this to the setting where you store previous data. Offline RL extends it further to the setting where you're just given some data, like in a conventional supervised machine learning problem, and then you're going to use that data you've been given to learn a policy. And this makes a lot of sense if you're imagining something like prescribing course of treatment for patients, because you don't want to do on-policy exploration in that setting, but you could perhaps obtain a lot of data from human doctors that have prescribed courses of treatment and use that historical data to learn policies. Okay. The second setting is data-driven model-based optimization, and I'm going to claim that this is very, very closely related. So this is a setting where there's some true underlying function that maps inputs X to outputs Y, and X is some representation of a design, something that you'd like to obtain. Maybe it is a protein sequence, or it is the a molecule for a drug, or it is the parameters of an aircraft wing, something that you're trying to select to attain some score. So Y represents how good that is. How fast does the airplane fly? How well does the drug treat the patient? Things like that. And we could imagine sort of approaching this problem a little bit naively to say, well, let's get a data set of designs and their efficacies. Let's get a data set of, let's say, proteins and how well they do at binding to a particular receptor. Take the designs as X, the efficacies as Y, and train a model. Those predictive models, those wonderful predictive models that Facebook and others have designed. Can we let's just train those up, and then let's optimize with respect to X, right? So we're going to train them up with empirical risk minimization, and then select the X that maximizes the learned model, F hat theta X. Many of you might already be guessing what the connection to reinforcement learning is. If you just replace F with Q and X with A, you're basically in the reinforcement learning setting. So what could possibly go wrong? These are very similar problems, and they share very similar challenges. So you can think of offline model-based optimization as basically offline RL with high-dimensional bandits, right? So, the word bandit is probably the correct way to make that connection. All right, so the problem, the major problem that at least I've noticed when trying to work on these issues is the distributional shift you get as a result of optimization. So if we have our protein problem, or our drug design problem, or our aircraft design problem, the problem of finding the best design involves taking the argmax of some learned function. And taking the argmax of a learned function, when that function is some highly expressive thing like a deep neural network, is known in the community to be a really terrible idea. Right? So we train this function with empirical risk minimization, the way we train anything. It'll work well on designs sampled from the training set, or from the training distribution rather. But then we could ask, well, is the probability under the training distribution of the optimized design of the argmax of X star, is that going to be high? Probably not, because we know that what can happen, and what does happen with large high capacity models, is adversarial examples. If you optimize an input to get a desired output, you're going to basically be fooling your network. You're going to be finding an input on which the network makes the largest mistake in the positive direction. And we know that such inputs exist. They exist for virtually all high capacity models, and they're called adversarial examples. So in a sense, this process of taking this argmax, it's virtually identical to the process people use to synthesize adversarial examples. So adversarial examples are what you're going to get when you do this. And it's perhaps most obvious if you imagine that X is high dimensional, like an image, but the same basic principle will hold even for lower dimensional X's. And certainly it'll hold for things like protein sequences. So optimizing with respect to model input might just optimize for the biggest mistake. In fact, I would probably revise and say not might, but will. So what I'll talk about today is the following. I'll discuss how we can, the kind of challenges that we get in offline RL that basically reflect this distribution shift due to optimization, how we can mitigate this challenge in the sequential reinforcement learning setting with an algorithm called conservative Q-learning, and how we can mitigate it in the model-based optimization setting with an algorithm called model inversion networks. And these algorithms are different, but hopefully what this will prompt you to think about is whether there's some crosstalk that's possible here, where algorithms in one domain can inform solutions in the other. All right, but let's briefly talk about, a little more concretely about how this optimization distribution shift issue actually crops up in reinforcement learning. So hopefully I don't have to go through the primer on RL. If you're in this workshop, I'm sure you're very familiar with this. You want to maximize expected reward. A very useful thing for maximizing expected reward is the Q function, because once you have a Q function, you can recover the greedy policy. And an optimal Q function satisfies the optimal Bellman equation, which means that you just have to make the left-hand side of this thing be equal to the right-hand side, which we often do by solving some kind of regression problem. So regress your QSA onto your target values, which are RSA plus max over the next Q, right? Standard Q learning. And this talk is going to focus basically entirely on dynamic programming. I know there's a world out there that is not dynamic programming that I'm just going to ignore, but that's because I have limited time. So we're going to be doing Q learning. All right, so what's the problem with Q learning in the offline setting? We ran some experiments. We're a very experimental group, so we don't believe in just the theoretical analysis. We want to see for ourselves. So we tried to see for ourselves, and indeed there was a problem. This is some work from about a year ago where we wanted to see what happens if you run. In this case, it's actually an actor-critic algorithm, but it's very similar to a Q-learning algorithm. It's just an actor-critic with a Q function. What happens when you actually train in the offline setting? And we were getting bad results. And in particular, we saw that the longer we train, the worse the results get. So we did what any reasonable machine learning person will do, and we surmised we must be overfitting. So we tried offline RL with different sized data sets. This is the half cheetah benchmark. Blue is 1,000 transitions, red is 1 million transitions, and they're both equally bad. So if it was overfitting, you'd expect it to get better as you increase the amount of data, and it doesn't. When we interrogate the Q function to ask it how well it thinks it's doing, it thinks it's doing great. So the y-axis here is a log scale. That red line, the 1 million data points, is at 10 to the 7th power. So it thinks it's going to do really, really well, and then is sorely disappointed when it's actually used to control the system. So what's going on? Why does it think it's going to do so well and end up doing so poorly? Well, this is that distribution shift problem. And to understand it in a little bit more detail, we have to recognize that what we're solving when we fit the Q function is empirical risk minimization. It's empirical risk minimization under a particular training distribution P of X. And if we train F under P of X and we're given some X star, we can ask, is F theta of X star going to be correct? F theta is whatever we're learning, Q function, model, etc. Well, we know that the empirical error under the training distribution is going to be low, but the expected error under some other distribution P bar is in general not going to be low if P bar is not equal to P. And even if X star comes from P of X, even then the error is not guaranteed to be low because we're not minimizing pointwise error, we're minimizing expected error. Now, the deep learning practitioner might say at this point, the caricature of a deep learning practitioner might say, well, we don't worry about this because neural nets generalize. So, you statisticians will make a fuss about distributional shift, but we've got neural nets and they generalize. And actually they often do, but there's a bigger problem here because we're not just going to be evaluating F theta of X on an out of distribution input. We're going to be selecting that input to be the argmax of F theta of X. And here's a picture to hopefully convince you that this is bad, if you didn't believe my adversarial example point from before. Let's say that this green curve is your true function, and the blue curve is the fit that you learned for that function. The blue curve is not too bad, like it's actually pretty decent in most places. But if you select the argmax, you get precisely that point that has the largest positive error. So even if you generalize well, even if you have a good model, if you're picking your input with an argmax, you're going to get into trouble. And where does that crop up in Q learning? Well, let's rewrite the Bellman equation in a slightly different way. Instead of writing it as a max, I'll write it as the expected value of the next Q value under a distribution pi nu, where pi nu is an argmax. So I didn't actually change anything. I just wrote it in a different way that made it a little clearer that you're evaluating an expected value. So that's your target value, that's your y. And how do you train Q? Well, you train it to minimize error in expectation under your behavior policy, which I've denoted here as pi beta. So you're regressing onto your target values under pi beta. So you would expect to get good accuracy when pi beta is equal to pi nu, right? Because then you don't have distributional shift. But of course, the whole point is to improve over pi betas, to get a policy that's better than whoever collected your data. So pi beta will not be equal to pi nu. And even worse, pi nu is going to be selected to maximize this expected value. So that's exactly the bad thing that we talked about on the previous slide. And that's why we get this massive overestimation. We're selecting the policy to maximize the Q values, which is essentially finding an adversarial example for our Q function. All right, so how has prior work gone about trying to mitigate this? Well, one way that people have approached this problem with some success is to constrain pi nu, to say, well, I'm going to not just pick pi nu to maximize the Q value, I'm going to pick it to be within some interval of pi beta. And that's a very reasonable thing to do. Does this solve distributional shift? Does it mean you get no more erroneous values? Well, sort of, but there are still a few issues. That said, this method has been quite popular. It's a fairly old idea to impose policy constraints of this sort, going back to natural gradient and things like that. But there are quite a few papers more recently that have explored this idea. It does have two issues. One issue is that this might be way too conservative. The reason it might be way too conservative is, imagine for a minute that pi beta has very broad support. Maybe it's just even a totally random policy. Now, constraining your pi to be close to a totally random policy means you just don't allow the agent to be too deterministic. That kind of seems like a bad idea. If you have broad coverage, that data set with broad coverage probably supports a much better policy than a totally random one. So this can be way too conservative. It can be partially mitigated with things like support constraints. Essentially, instead of constraining the distributions to be close, you can constrain their supports to be close, and that can really help. But it doesn't fully address the issue. The second issue is that estimating the behavior policy itself for the sake of enforcing this constraint can also be difficult. So if your data was collected in a synthetic experiment by another reinforcement learning agent, then getting pi beta might be pretty easy. But if you're talking about the medical treatment setting where the data was like human doctors doing stuff, you don't know what policy they were employing, and just copying their behavior with by fitting a policy pi beta might already be pretty challenging. So this can be a serious issue in practice. And again, it can be partially mitigated. There's some tricks, like, for example, you can have implicit constraints that don't require knowing the functional form of pi beta, but only require samples. And those can work to a degree, but it's still a challenge. So what I'm going to talk about next is an algorithm that perhaps more directly attacks the cause of the problem, the distribution shift due to optimization. And this is an algorithm called conservative Q learning. So the problem is that we have this massive overestimation because we're essentially optimizing against our Q function and fooling it into thinking that we can get a high value. So that's this problem. And the way we're going to mitigate it is pretty directly. We're going to take our original fitting objective for our Q function, and we'll combine it with a regularizer that explicitly finds the Q values, the actions with high Q values, and pushes them down. So in this regularizer, there's an action distribution mu that is selected adversarially, and the Q values are minimized under mu. So that the whole point is to basically find these peaks and push them down. It's a very blunt instrument. It's a pretty direct way to just directly find those erroneously high Q values and drive them down so that they're not so high anymore. Now, this blunt instrument can actually be shown to learn a lower bound on the true Q function if you choose the regularizing parameter alpha appropriately. So you can show that if you learn Q hat pi in this way, it'll be pointwise less than or equal to the true Q pi under some technical assumptions for a large enough alpha. That suggests a pretty straightforward algorithm for doing offline RL. Simply alternate between learning your lower bound Q function and improving your policy to maximize that lower bound. And then hopefully you wouldn't overestimate. Now, the bound can actually be improved substantially. If you're just driving down the large Q values, you're going to drive down the Q values that are mistakenly large. You'll also drive down the ones that are correctly large. So there's a more nuanced bound that tends to work a lot better. And the idea is to take this term that always pushes the Q values down and add a second term that pushes them up. So notice here there's a negative sign. The Q values are pushed down under mu, which is selected to find the large Q values, and they're pushed up under the data distribution. So the idea is that if your large Q values are for actions that are similar to actions in the data set, these two terms should cancel out. So the in-distribution actions should not get pushed down. But if you have large Q values for out-of-distribution actions, then the first term will push them down, and the second term will push something else up. Now, it's actually no longer guaranteed if you use this objective that you will get a pointwise bound. However, somewhat surprisingly, we can still show that you get a bound in expectation under your policy, which means that you're bounding the value function. So you still get the result that if you learn your Q function in this way, the resulting value function will be a lower bound than the true value function for a large enough alpha. So you minimize the big Q values, maximize the Q values in the data set. The full statement of the theorem that's in the paper is shown here. It's a little bit involved, but let me just briefly summarize. There's essentially three terms. We're saying that v hat, the learned value function, is less than or equal to the true value function minus alpha times some positive pessimism term due to the regularizer, plus an error term due to sampling error. And alpha just needs to be chosen large enough so that this pessimism term overpowers the sampling error term. And if that's the case, then you get a lower bound. Okay, so does the bound hold in practice? We measured this empirically, so the numbers that I'm going to show you are the expected value of the learned Q function with CQL minus the Monte Carlo estimate of the true Q function. So if these numbers are negative, that means that we're underestimating. If they're positive, then we're overestimating. And here are the results. So CQLH is the final method that I showed. CQL equation 1, that's the initial method that just has the minimization. And you can see that both of the CQL variants give lower bounds, although the more advanced version gives a much tighter bound. And then most of the prior methods, things like ensembles and policy constraints, actually are still wildly optimistic in comparison. We evaluated this on a range of benchmark tasks from the D4RL dataset. So D4RL is a dataset for evaluating deep offline RL methods that we devised that has tasks like maze navigation that require stitching together parts of different trajectories, more realistic robotics tasks like dexterous manipulation, as well as some driving and traffic control tasks. So if you're interested in evaluating your offline RL methods, I highly recommend it. This is getting to be a pretty popular data set. When we looked at how CQL compares to prior methods, and this was done back in May, so better methods have come out since then, but at least back in May when we tried this, one of the things we found was that, for some of the harder tasks like the maze navigation that requires stitching together parts of trajectories, most of the previous methods, things like these policy constraint methods, really didn't work very well. So these scores are normalized between 0 and 100. On some of the robotics tasks, the strongest baseline was actually just behavior cloning the data set. So that means that the RL part of the offline RL just wasn't helping all that much. CQL, by comparison, actually did very well across a range of these tasks, up to 5 times better on some of the dexterous manipulation tasks, 50 to 300% better on some of the others, and in a sense, infinitely better on the maze tasks because it was the only method that was able to make some progress. Same story in Atari games. So it seems like it works quite well across many of these tasks. And we also seem to have some idea for why it works because of this lower bound property. Of course, there's still plenty of room for improvement. As I said, these scores are normalized between 0 and 100, so there's still a really long way to go. All right, so I talked a little bit about how we can have this minimization trick to address the issue of optimism that occurs because we're optimizing against our learned function. Next, let me talk a little bit about model-based optimization, where I'll describe a different approach, but hopefully it'll be apparent how these different methods might be applicable to both domains. All right, so here we're going to be dealing with predictive modeling and design. So the setup we're concerned with, we collect data from previous trials. Data consists of tuples of x and y. We learn a mapping from x to y, and then we're going to use that mapping to find the best x. So if this was a Q function, we would be doing RL, but we're just going to be doing design. We could optionally collect more data, but we're going to focus on the fully offline case here. So what's wrong with just doing prediction? Well, I've mentioned this before, but essentially the problem is that when you optimize your new design to find the argmax of the learned function, you might get an out-distribution input or an adversarial example. We can illustrate this like this. Let's say the x-axis is your design, maybe it's your protein. This is the true function f of x, and there's its optimum. You get a data set. Maybe the data set is represented by these green dots. You fit your function to those green dots, and you hope that you get something like this. So you hope that your fitted function f hat theta has the same optimum as the true function. And then when you optimize it, instead of optimizing the true function, which you don't know, you optimize f hat theta of x, which you do know. And hopefully your design, is close enough to your data set that you get the correct answer. But if your f hat theta of x extrapolates or generalizes in some unreasonable way, then the argmax might be very far from a good design, and it might actually have very bad performance. So you somehow need to keep your design close to your data. So somehow you need to figure out this region where you can trust your function and stay in that region, right? So can we somehow maybe estimate the training data distribution and stay close to that training data distribution? This would be the equivalent of a policy constraint method in offline RL, but now applied to this design problem. It turns out that this is actually very hard to do in high dimensions. In fact, if your learned function f hat theta of x is susceptible to adversarial examples, your learned density estimator can also be susceptible to adversarial examples. So there's a paper called Do Deep Generative Models Know What They Don't Know? The short answer is no. And this is a quote from the paper. We find that the density learned by flow-based models, VAEs and pixel CNNs, cannot distinguish images of common objects such as dogs, trucks, and horses from those of house numbers, assigning a higher likelihood to the latter when trained on the former. So it's not a great idea to use density models to estimate these confidence regions, because the density models themselves can be fooled. So what can we do? Well, we would like to maximize f hat theta of x subject to a constraint that our x's are in distribution, but this is hard because x's are very high dimensional, and it's easy to find invalid x's that will fool our density, right? It's easy to find these adversarial examples. But here's an interesting observation. Our output y is one-dimensional. So finding valid values of y is very easy. If you have a one-dimensional variable, you can just discretize it and just see where you have higher density, and that's very easy. You can't fool that because it's so low dimensional. So what if instead of learning f hat theta of x, we learn f inverse of y? Instead of mapping from x to y, we learn to map from y to x. And then we can find in distribution y's very easily because y is just a scalar value. So then we're going to select x star to be f hat inverse of y for the largest y that is close to the data. And that can help us alleviate this distributional shift problem. It's still tricky to choose the y that is close to the data, but it's much easier than before because y is just a scalar value. So we call this model inversion networks because they aim to invert the model. All right, so one problem here is that f inverse of y is one to many. In general, for any given fitness value, there might be multiple designs that attain that fitness value. So we're going to approximate f inverse of y with actually a stochastic function. We're going to have a neural net that takes in the y and also a noise sample z. And the idea is that for different z's, you'd output different x's. So for a given base distribution over z's, we want to cover all the x's that take on that value of y. So z is just a random number. And the way that we're going to train this thing is, well, we need a generative model that turns random z's into x's. And it turns out that GANs do exactly this. So generative adversarial networks, they take in noise, they output a sample from your data distribution, and we're just going to train a conditional generative adversarial network. So these are great for generating faces. They've also been shown to generate things like proteins and other more relevant things for this discussion. So we're going to choose x star, we're going to train f inverse as a GAN. So it's going to be a function that takes in y and z, and we'll choose x star by just asking our f inverse of y to generate the x for the largest y that's close to the data. Now, a simple way to choose y would be to choose the best one in the data set and then slightly increase it. But we can do it a little bit better if we choose y such that an inverse and forward model agree with each other. So we'll actually optimize over both y and also z, the noise, to find the largest y so that when you take your y, feed it into f inverse, and then feed it back into your learned f, you get back the same y. So you're going to maximize that subject to the constraint that the y that you start out with and the y that you get from inverting it and then sending it back forward agree with each other that are within epsilon. And that will give you in distribution y's that are hopefully as large as your data set will support. Okay, and since the y is 1D and all the z's are in distribution because that's just your base noise distribution, this is all okay to do. So you're not going to generate adversarial examples by doing this because y is 1D and all the z's are in distribution because it's just noise. So putting it all together, we take our data set, we train an inverse model with a GAN, we train a forward model with just mean squared error, we find the y and the z where the forward and inverse models agree with each other, and that's our final design. I'll go pretty quickly through experimental results since I don't have very much time, but we applied this to a protein design task borrowed from a paper by Brooks et al., where this thing works pretty well. It can also generate faces. So in the face generation experiment, the goal is to generate the youngest face. So you've only seen faces that are older than 15 years of age, and it's trying to generate the youngest face. And the faces look a little messed up, but in subjective human studies, humans do rate these as being younger than the youngest face in the data set. So it seems to be applicable to high dimensional problems like faces, as well as more relevant problems like protein design. But the bit that I want to talk about very briefly at the end is a little bit of takeaways. So I talked about how data-driven optimization can handle these high-dimensional design spaces, but simple predictive models are not enough because of that optimism issue. Effective data-driven optimization requires some mechanism to account for the accuracy of the model for candidate input, and these inverse models can make this substantially easier. Now, an obvious question that might come to mind is that I discussed two different techniques for dealing with this optimism problem, the conservative Q-learning approach and this inversion approach. Could we imagine using something like CQL to address this problem as well? Very likely, yes. In fact, that's something we're working on now. I just unfortunately don't yet have results to show you. So some concluding remarks. Well, we should think about making decisions with data. I think that's a really good idea, and hopefully it's something many of you are thinking about. RL already sort of does this, but it's not just an RL problem. It crops up in bandits, model-based optimization, etc. And the issues, I think, in many cases are much the same. Making decisions with data is really powerful. Especially if you can support big models trained on big data sets and get powerful generalization. And the techniques in question, I think, are going to be very similar for a bunch of these domains. They basically boil down in many ways to this issue of distributional shift due to optimization. And we can imagine constrained distributions, avoiding overestimation, these conservative tricks, inversion tricks, etc. And many of them are likely to apply to both domains. All right, thank you very much. And I'd be happy to take any brief questions.
Okay, great. Fantastic talk. So maybe maybe one quick question before we move on to the panel. I don't see anything in Q&A. Maybe a clarifying question for me. I mean, the plots I saw, like your very first plot where you showed the problem of overestimation, I saw the value being overestimated, but not the maximizer. It's harder for me to visualize.
Yeah. So it's it's sort of looking at the end result rather than the intermediate phenomena. So the intermediate phenomenon is a little harder to track down because the Q function is conditional, right? So it's going to make different predictions at different states. In some states, it might not actually overestimate. But the trouble is that because you're backing up these values, if you overestimate massively in even one state, that overestimated value then propagates through the rest of the MDP. So, as soon as the bad thing happens in one place, it sort of infects everything else.
Yeah, it'd be nice to somehow visualize that. But yeah, I can definitely imagine.
Yeah, we have a little bit more visualization in the paper in like a grid roll domain. I didn't find it to be quite as interpretable as this, but that maybe would be helpful.
Cool. Okay, well, thank you again, and let's organize for our panel.